All right. Morning, everyone. We welcome everyone to the 2024 IEEE Online Forum on Climate Change Technologies, and we thank everyone for participating. And just a few reminders, and please submit your questions in the comments and chat box. We will not share the presentations, but instead please check back in the website for on-demand recordings. So we request participants to mute the microphones, and if there are any bandwidth issues, switch off the video as well. I'm happy to introduce our first speaker of the session, Professor Thomas Brown. Professor Brown is a leading academic at the Department of Electronic Engineering at the University of Rome. He earned his PhD degree from the Cavendish Laboratory, University of Cambridge, UK. Professor Brown is an expert in the large array electronics with particular emphasis on organic transistors, e-paper, organic LEDs, and solar energy generation. In the past, Professor Brown received a re-entry fellowship awarded by the Italian Ministry of Education, University and Research. Professor Brown is a founder and director of the Center for Hybrid and Organic Solar Energy at the University of Group at the University of Rome. His current research focuses on perovskite solar cells for light harvesting indoors on flexible substrates and on biohybrid devices. With this introduction, I welcome Professor Thomas Brown on the stage to share his expertise on the titled Photovoltaics for Indoor Energy Harvesting.
Thank you very much for the kind introduction. It's a pleasure to be giving a presentation at the IEEE Online Forum on Climate Change Technologies. I'd be speaking in the next 40 minutes on the topic of photovoltaics for indoor energy harvesting. So photovoltaics is mainly developed for the outdoors. So I'll show you what are some recent developments, especially in perovskite solar cells for indoors and why they could be interesting for science, technology, and our society. So I'm from the Department of Electronic Engineering and from the Center for Hybrid and Organic Solar Energy, which is a laboratory of around 450 square meters in the outskirts of Rome, where we develop perovskite solar cells, polymer solar cells, dye-sensitized solar cells, bihybrid devices, and other type of devices connected to energy, such as supercapacitors. So here's the outline. I'll talk about indoor PV, the markets, and the illumination conditions. Then I'll look at some of the main differences in strategies for the design of photovoltaics for outdoor versus indoor. And then I'll be focusing mainly on the customization of perovskite photovoltaics for indoors, mainly through bandgap engineering and interface engineering. Then I'll go on to show some examples of possible applications, give an overview of the R&D for different PV techs and some challenges for the future. And some of this content is published in a recent nano energy review paper for anybody who's interested. So the photovoltaics market, as I mentioned earlier, is mainly for outdoors. So solar farms, megawatts, building integrated, kilowatts, some solar cars. And the field, the market has been growing tremendously in the last 10, 15 years, and prices have dropped. On the right, you can see that silicon dominates the market. Before it was polysilicon, and now mostly it's monocrystalline silicon. Thin film takes up less than 5% of the market. So silicon really is the main actor for outdoors. Now, why indoors? The idea is to harvest artificial light that's already inside the buildings to illuminate them for human purposes. And so one can think of giving power to electronic devices, low power ones, like those of the Internet of Things, IoT. So smart sensors like movement sensors, temperature sensors, fire sensors, smoke sensors. And the idea is to replace batteries and so have a more sustainable energy source and also a more reliable one in time, because you don't have the risk of the battery losing its power and not giving power to some important sensors that can be implemented in buildings. So the idea, as shown in the bottom left image, is to connect the PD device to a power management unit. Could be an MPPT, impedance matching unit, a boost or buck converter to increase or decrease the voltage, a super capacitor or battery to store the energy, and then a buck or boost converter to set the output voltage that can power the electronic product. And this is the power needed by the electronic product in time. So most of the time, the electronic product would be in sleep mode. So power would be very low. But then it would start sensing and transmitting the reading to a receiver. That's where the power output will increase. So that's why developing PV devices with storage units can be important. So one can size the PV devices not for the maximum power output, but for the average over time. And according to how much power you can develop with a PV device, you can start powering a greater number of devices. And here there's some examples, like a watch, a real-time clock, which only need between tens and hundreds of nanowatts, a calculator, microwatt, communication technologies like LoRa, 10 microwatts, wireless sensor nodes, 100 microwatts. So whereas we need hundreds of watts and kilowatts for our home, actually for these low power electronic products, we need much less. Other application examples are top left, a table with PV, so that can have a large surface area to, for example, recharge smartphone batteries. This is an e-beacon, so something that can transmit information to nearby people, say museums or in shop malls. This is a solar-powered thermometer, Internet of Things, smoke sensor with a flexible PV module, portable, rollable PV module to charge electronic products, and also shelf electronic labels. So electronic labels that can be found in supermarkets. These are examples of two products being developed by two companies focusing on indoor PV. The indoor PV market has been growing very rapidly. And on the left, you can see that the indoor PV market is reaching around the $1 billion in 2024. The number of IoT connected devices is also growing rapidly. This is in a semi-logarithmic scale. And in the future, the number of IoT devices compared to the total of electronic products will be increasing a lot. So there's going to be a massive need for generating power for the IoT. That's why finding energy harvesting technology can be a key enabling technology also for the IoT. So let's look at what the conditions are, specifically in relation to the differences with the outdoors. So in outdoors, there's what is called a standard test condition or standard test conditions, where the temperature is defined at 25 degrees centigrade, the irradiance at 1,000 watts per square meter, and the spectrum is given by the mass 1.5. And so this can be found in tabular form, can be downloaded and used. And you can buy solar simulators that simulate these spectra. Now, indoors, lighting has been developed for the human eye. So rather than talk about radiometric units, the lighting industry uses mainly photometric units. So the difference is that the radiometric parameters are convoluted by the luminous efficiency function, which is the sensitivity of our eye in photopic conditions. So when we see color. And so instead of using radiant flux, we use luminous flux, lumens. And instead of irradiance, watts per square meter, we talk about lux. And there were 4 main light bulbs till recently, which were the incandescent, the halogen, the compact fluorescent, and the white LEDs. Now the incandescent is not available anymore because it's not energy efficient. The 2 main light sources are LEDs and compact fluorescent lamps today. And whereas the incandescent had most of its power generation in the infrared, today's lamps like compact fluorescent in purple or LEDs in blue are focused in the visible spectrum, so they can be very efficient in terms of utilizing the sensitivity of our eyes. And there's very many different types of lamps found in the market. And one of the main parameters, the correlated color temperature. So high correlated color temperatures, say above 5,000 Kelvin, are what are called blue or colder lamps. Whereas the lamps used for residential areas are mainly warmer, just because they have the feel of the incandescent lamp. And in spaces like shopping malls or supermarkets, the color temperature is more towards the neutral. So we conducted a study where we see that in residential areas, most of the correlated color temperatures sold by online vendors like Amazon is around 2,700 Kelvin, whereas for office and commercial spaces, it's more around 4,000 Kelvin. Now, the IEEE has come out last year, July 27th of July 2023, with a technical specification which gives some recommendations on how to measure photovoltaic devices indoors. Their example are white LEDs or compact fluorescent lamps at 5,000 CCT. What about the luminance levels in indoor environments? So in homes, the lighting, so the luminance levels are around 100 to 200 lux. Whereas in offices, where you need to read, write, and so on, the luminance levels are higher, around 500 lux. In retail spaces, you can find 1,000 lux. Whereas on walls or ceilings in rooms where there's not really direct light, the lux levels are around 50 to 80. So there's a broad range of lux levels which need to be considered when both developing photovoltaics and also implementing and applying them indoors. So 50 lux can be considered low light, 200 lux living room, 1,000 lux supermarkets. And actually, these are the three main lux levels which are recommended to test your photovoltaic devices. So if you're working on photovoltaics and you want to address their performance, these are the three main levels which are recommended. And the optical power density, going back to the radiometric units, are between 30 and 160 microwatts per centimeter square. These are between 2 or 3 orders of magnitude lower compared to the standard test condition, which simulates sunlight. So 100 to 1,000 times less intense than sunlight. So this needs to be taken into consideration when developing PV. So let's look at the design now of PV outdoor versus indoor. So we started working on indoor PV around 10 years ago. And here we are testing commercial devices. So polycrystalline silicon device, which is this one. And the efficiency under standard test condition was 15%. So at that time, it was an average efficiency for polycrystalline solar cells. Now they've gone up to 18, 20. Then we tested amorphous silicon. Yeah, so these are the 3 amorphous silicon modules we identify in board. And actually, amorphous silicon is the main commercial technology for indoor PV. The efficiencies were between 1% and 5% under sunlight, so standard test conditions, which is much lower than polycrystalline silicon. So why are they used for indoors? Well, we then measured them under a fluorescent lamp at 200 lux, which is the residential area typical lighting conditions. And you can see why. So the polycrystalline silicon cell, the efficiency dropped from the 15% under sunlight to around 4% under this lamp. Whereas some of these amorphous silicon devices increased to beyond 8, 9, almost reaching 10%. So, double the efficiency of crystalline silicon indoors. So there's a huge increase. So what's the reason? Why is amorphous silicon working better than polycrystalline silicon for indoors? Well, we can start looking at the Shockley equalizer limit, the detailed balance limit, which tells us what is the maximum efficiency obtainable from a single junction, so just one material device. So to simplify things, you have a semiconductor and with a valence band and a conduction band separated by the energy gap. Now let's assume all photons are absorbed above the energy gap and none below the gap. And the current is equal to the photon flux, which can be calculated by the AM 1.5G spectrum, which is tabulated, just by dividing the irradiance by the energy of the photon. So it's very easy to do. And so let's say each photon creates an electron. That's how you get the current available. The voltage is equal to the energy gap, the maximum voltage. Well, then you get a curve which tells you what's the maximum theoretical efficiency. Now, if you put some of the main inevitable losses, the calculation gives you a 30% efficiency as the maximum theoretical achievable efficiency by a single junction solar cell. And the best energy gap is between 1 and 1.5 eV. So silicon is very good for outdoors. However, indoors, the spectrum are much narrower and concentrated in the visible, so between 700 and 400 nanometers, so between 1.7 and 3 electron volts in terms of energy. So being much narrower and towards the visible with no infrared, then you can do the detailed balance limit again, and you see that the best band gap is around 1.8, 1.9 electron volt, not between 1 and 1.5. And the efficiency increases to over 50%. So more than half of the optical energy or the optical power can be transformed into electrical power. That's why, you know, indoor photovoltaics can be so exciting. And amorphous silicon, when it's hydrogenated, which it is in commercial products, has a band gap of around 1.7 eV. That's one of the main reasons why the efficiency jumps when going from outdoor to indoor illumination. So polycrystalline 1.1, amorphous silicon 1.7, and these jumps. Amorphous silicon also has a high shunt resistance. So the other thing we need to consider, if this is the equivalent circuit, so this is the shunt resistance, which leads to recombination losses. This is the series resistance, which leads to drops in voltages and fill factors. Here, there's a plot of the output power versus intensity for different shunt resistances. So at high intensities, so those found outdoors, the effect of the shunt resistance isn't very great. At very high intensities, you know, if you have a shunt resistance which even changes by orders of magnitude, you see no effect. Whereas at low intensities, the effect of the shunt resistance is huge. So to develop efficient photovoltaic cells for indoors, one needs to be very careful to have very high shunt resistance and minimize recombinations. So silicon dominates the PV market. What about indoors? So recently, in June, I went to this conference in Perugia, and it was very interesting because there was various even commercial developers of either power management IC units or of photovoltaics. And there was many different technologies, PV technologies, which were being demonstrated. So this was a dye-sensitized solar cell, organic solar cell, perovskite solar cell, amorphous silicon. So for developers of PV, the race for which technology will become dominant is still open. There's a lot of development of different technologies for indoors. And so we've been working on perovskite PV, and I'll show how to customize perovskite PV for indoors through bandgap engineering and interface engineering. So perovskite materials are given the name perovskite since Gustav Rose in 1839 named the mineral towards the Count Lev perovskite name, and it was calcium titanate. But there's methylammonium lead halides, where the A large cation here is the methylammonium ion. The small cation B is lead, and X, the purple ones here, iodide or bromide halogen ions. These have attracted a lot of interest in the last 15 years. Between 2009 and 2011, they were being used for replacing dyes or together with dyes in dye-sensitized solar cells, but the devices didn't really work so well because of the electrolyte. Then Snipe and Gretzel group in 2012 used a solid state configuration and achieved over 10% efficiency. So that was a major breakthrough. And things have been improving over the years. And just in 2014, the first certified power conversion efficiency of over 20% was produced by CRICT in South Korea. Now the efficiency is over 26%. So why perovskites, methyl ammonium lead iodide perovskites? They have high absorption coefficients, so only a few hundred nanometer thickness of the semiconductor is used. High diffusion lengths, and which are of the order of the film thickness, and they can be processable in solution, so they can be printed. So the device structure is transparent substrate like glass or PET, ITO, transparent conductor, compact TiO2 layer or SNO2 layer, sometimes a mesoporous scaffold so that the perovskite can grow over it. The perovskite film in brown, a whole transport layer, and a top electrode, which could be gold or carbon, for example. So we tested 3 different devices where the TiO2 layer was deposited by spray pyrolysis, by sol gel, or by atomic layer deposition. The atomic layer deposition of the TiO2 did improve device performance, but all 3 types of devices had an efficiency of between 10 and 16%. When we measured the same devices under compact fluorescent lamp at 200 lux, so very low intensity, the devices with a spray pyrolysis deposited TiO2 did not work. So there's efficiency 0. The FTO sol gel did work, but efficiency was around 3%, so much lower compared to AIM 1.5. Whereas the ALD ones, the best efficiencies reached 25%. So that's double the performance under one sun. So we were very surprised. This was the first of our studies and the second published paper on perovskite for indoors. So the reason is, of course, low density of defects. The band gap is 1.5, 1.6, which is good. And the spectrum of LED is much less broad compared to the sun. Why did ALD deposited layers work so well? Well, for the sol gel devices, you can see there were pinholes. So the shunt resistance suffered. And you can see that in the dark currents. So actually, the recombination currents was as high as the forward currents. Whereas for ALD devices, hardly any pinholes. I mean, they weren't visible in this AFM. The recombination current was 3 to 4 orders of magnitude lower compared to soldier. That's why they work so well. So they're blocking recombination of holes and electrons at this contact. Recombination currents need to be much less than photo-generated currents. So because the optical powers under 200 lux are very low, you want recombination currents to be at least 10 to 100 times lower. Actually, we find that 100 is a good factor because below that, the efficiency isn't so good. Above that, you can get good efficiencies. So you need recombination currents to be 100 times lower compared to the photo-generated ones to achieve good efficiency. So that's interface engineering. The other thing you can do is, as we've seen, increase the band gap, because you want to go towards 1.9 electron volts, which is the theoretical best for indoors. So via compositional engineering, you can change the band gap of perovskites. So you replace iodide with bromide. You can go from X equals 0, so fully iodide, to X equals 1, fully bromide. And you can see the absorption cutoff goes from 120 to 547 nanometers. So the band gap increases with bromide content going from 1.5 here to 2.3. So we developed these films and constructed solar cells, perovskite solar cells, hoping we get the best efficiency at 1.9. But actually, we do get an improvement in efficiency going from 0 to 17% bromide. So the band gap goes from 1.5 to 1.66. But after that, the efficiency goes down. So we needed to understand why. So we carried out SEM microscopy and looked at the grain sizes and also at the separation between the grains for these films. We looked at the recombination currents versus the forward currents, and also the shunt resistance over the series resistance. And to summarize, we found that to achieve high efficiency perovskite devices, you needed an average grain size to be higher than 300 nanometers. So more than 70% of the film thickness. This will allow you for the photo-generated carriers to go to be collected at the electrodes without finding many grain boundaries where recombination takes place. Intergrain spacing needs to be much less than 10 nanometer. The J on over J off needs to be greater than 100. And the shunt over series resistance ratio needs to be higher than 100. So that's the reason why you don't get the highest efficiency here, is because for high bromide content, you start to get defects arising in the film, which lower the efficiency. One thing we're very interested in is also to develop solar cells on flexible. The reason is they're more portable, they're lightweight, and they can be easily integrated over any surface, even curved, which of course, if you want to coat your electronic products or your furniture, your home with photovoltaics, then something that's thin, conformal is the best option. So we made the first flexible cell for indoors. We also use flexible glass. And recently, we use PET, which is the main substrate plastic substrate for organic electronics. And we deposited SNO2, the perovskite. Then we processed it with a molecule called tetrabutyl ammonium bromide, TBAB. Then deposited the whole transport layer, spirometers, and the metallic contact on top. So if we use zero bromide, so the standard perovskite, the efficiency was around 13–14%. When we increased the bromide content to 17%, we achieved an efficiency increase of 42%, up to around between 20 and 24%. When we applied the TBIB, which is interface engineering, the efficiency increased by a further 26%. And the efficiency on these plastic devices was around 32% at 1,200 lux, around 29% at 240 lux. So one for like supermarket environments and the other for homes. So we talked about why there's a jump increasing the band gap. Why is there a further jump when you do interface engineering? Well, we teamed up with groups who carried out GWAX and XPS. We found that the TBIB was creating a one-dimensional perovskite here, which is more stable, leads to less defects. And you can see that by the transient photovoltaic decay, where this time increases, leading to lower recombination probability. And actually, TBIB also increases the lifetime of the devices. So at the time, which was a year ago, these were the highest efficiency devices on PET. Okay, so let's look at some examples of possible application and sizing for PV. So I chose the group by Francesca Brunetti et al. Did some flexible modules, and the efficiency was between 13.8% and 15% indoors. And these were used to power an electronic system consisting of RF printed antenna, a silicon chip, a P-dot strain sensor. So if you bend it, the resistance would change. And if you look at this video, there was a smartphone application which read the strain, so the resistance value in the P-dot layer here. And it gives one reading when the light's off. When you switch the light on, the RFID system becomes active, and the number of readings are 23. So by giving power, you've increased the number of readings by a factor of 20. So that's why, having power can be useful. And we did a calculation based on some Fujikura technical review data. And at 1,000 lux illumination with cells with 30% efficiency, you can think of developing a temperature humidity sensor just with a module of 1.6 centimeter per side. Human sensors, you need 2.5 centimeter. These are proximity sensors. Or you can take an image every 10 seconds with a still camera with 3.1 centimeter per side. So the bigger the device, or the more efficient the device, the more products you can operate. Of course, this was assuming a 10-second cycle. So if you can produce more power, you can have higher frequency, or if you want less power, you can go from 10 seconds to more seconds. So in the last couple of slides, I'll give you an overview of the R&D for different PV techs. So as we said, silicon isn't the main technology for indoors, but these are deficiencies which have been reported in the literature. So this is the perovskite. Now there are reports of above 40%, which is the highest reported for any technology. Compound semiconductors are also above 40%. DSSCs and OPV are above 35%. So these emerging PV technologies have a lot of potential for entering the photovoltaics market for indoors, because the efficiency is much greater than what is now the dominating technology, which is silicon, and could be an entry point, an entry market for these technologies until they're ready to compete with silicon for high volume markets outdoors. And these are the number of publication in recent years over the years. And you can see there's been an exponential growth in the last 5 years, most of it on PV development. And, in yellow, there's perovskite, green DSSC, and purple OPV. So these are the main technologies that are being studied in academia, growing exponentially. What are the challenges for the future? Well, most of what I've shown you is carried out on small laboratory cells. So one needs to upscale, and upscaling, keeping the recombination probabilities and recombination currents and low is key, because there's much more probability of creating defects also at the interconnections between cells. Also, you need to develop geometries which are good for low light rather than intense light. The other is the operating conditions. So on one hand, indoors, there's no UV or hardly any UV. The temperature differences are less compared to the outdoors. There's no hail, storm, rain. And so the environment is much less harsh, which is good for emerging technologies where stability is still an issue, like perovskites, OPV, and DSSCs. On the other hand, and here we show a study we conducted on DSSCs, if there's any aging in the device, you'll see it more under low light conditions, because defects, of course, give rise to more problems, because recombination currents can become closer to the photo-generated currents, which are very low. So more needs to be done to understand these conditions. So in conclusion, I've shown you differences in indoor design versus outdoor. You need higher energy gaps, lower trap densities, how you can customize indoors to have high efficiency, over 30% in both on glass and PET. What are the challenges? And what are some applications for this technology? The interest in the field is growing rapidly. And finally, I thank all the collaborators for the work I've been showing. And these are the names of the people who've carried out the work at shows, the collaborations, the funding agencies, and I thank you for your attention.
Thank you, Thomas, for the interesting talk.
Thank you.
It's time for take some questions. I think we have some questions from Charlie in the chat box. Thomas, can you see that, or should I read it for you?
Yes, if you can read it, please.
Yeah, right. Okay. So the first question is, Silicon carbide has a band gap of 3.3 electron volt, and he's asking, can it be used for indoor applications? And he's suggesting that silicon carbide is very expensive.
Yeah, so silicon carbide is 3.3. That would be absorbing only in the ultraviolet.
Mhm.
So it wouldn't really be useful for indoors because the indoor lighting doesn't have UV component. So silicon carbide, is very good for high temperature applications because it's got a high band gap. But yeah, there's hardly any UV in white LEDs or compact fluorescent lamps.
And the production cost also very high for silicon
Yeah.
carbide compared to, yeah. And the next question is from Charlie is about the comment about your supercapacitors. So he's asking, do they use exotic materials like lithium or cobalt for batteries, or how long they can hold the charge, the supercapacitors?
Well, that's a good question. Unfortunately, I'm not in the supercapacitor field, so I wouldn't be able to answer that question. I know there's a lot of work being carried out, and some groups, including some researchers in our department, who are working on them. Because of course, if you can develop both the storage element and the power generating element, then you got the whole energy generation and storage package at the same time. And I've seen some talks where there's a lot of different materials being used, but I can't say more than that.
So yeah, it's a fast charging technique.
Yeah.
And the next
Good
question is
fast
from,
charging.
yeah,
I
the
mean,
next question. Yeah, the next question is from Charlie is saying perovskites were radiation hard for space applications compared to silicon. Is that true?
yeah, so there's been a lot of interest recently also for space applications. And so one of the, surprising or amazing properties of perovskite is when it has defects, they kind of produce states which are not inside the gap or near the middle of the energy gap.
Mhm.
So these defects don't really affect so much the performance. And there's been some studies which have shown the resistance to the kind of particles found in space. The other issue which leads to degradation of perovskite is water vapor, and of course, in space you don't have any water vapor,
Yeah.
so that could help keep the lifetimes high.
Oh, thanks. There's one more question from the participant. I'm not able to read the name properly. It says KJS. The question is, isn't there UV indoors if you have any open windows, example, summer?
Yeah, so that's a good question. So one of the biggest issues I think with indoors is the fact that as the one of the members of the audience was saying, is the lighting conditions depend strongly on where you put it. So if you put it next to a window, it will see very different lighting conditions compared to, say, you put it next to a desk where there are no windows. And so for both the people who want to use them and also for people who want to develop them, it's tricky to define these different conditions. Yeah.
Right.
And I'm working with a PhD student and trying to understand how to predict the lighting conditions in
Mm.
a room environment. That's a very interesting topic because,
Right.
of course, you need to size these photovoltaic devices. But how do you size them if you don't know the lighting conditions.
Hmm.
So yeah, it's a kind of topic that needs to be addressed if you want this technology to really make it.
But in general, photovoltaics, I mean, perovskites are sensitive to UV radiation, or I mean, is it easy to tune them for UV
Well,
radiation?
yeah, they are sensitive to UV radiation. And in fact, you know, the best way to use perovskite even for outdoors is probably to put some UV filter
Oh,
when they're used outdoors.
okay. Does UV light affect the stability of the material, or is it
Yeah,
stable? Okay.
yeah,
That's it.
UV can
Okay.
affect it, but especially in combination with water vapor and other um, ingress of gases.
Right. Okay, so there's no other questions in the chat back. So I have a few questions from your talk.
Yeah,
One general question is, if you want to extend this indoor PV to automotives, do you
yeah.
see it's a direct extension of what you're doing, or do you need to do anything extra to fit into that domain?
Yeah, that's interesting. So for the automated business, so there's two sides. One is facing the sunlight. So there you'd develop the technology for standard test conditions. Of course, indoors you could develop for, so if it's facing indoors, then you could think of low light, but that
Mm.
would still be probably more diffuse light from the sun
Mm.
rather than artificial light, because
All right.
yeah, the artificial light you use very little.
Mm.
So maybe you could develop a low light device, so works well in low light, but instead of tailoring the band gap to the artificial light, you still develop it for diffuse sunlight. So that could be
Oh,
a third type of technology.
yeah, yeah.
Diffuse
Yeah,
sunlight.
yeah, yeah, right.
Yeah,
It's far away to think, but yeah, electric vehicles are really on the
yeah,
road
yeah.
now. So
So yeah, so you could, you know, switch off your car and at least have electronics working.
yeah, true.
Yeah, that's a great idea.
Right. And the next question is how would stability of the perovskite indoor compared to the outdoor? Is it the stability in terms of performance? Yeah.
Yeah, so that's very good question. So indoors, the environment is less harsh. So there's less temperature variation, less humidity variation. There's hardly any UV because it's, you know, diffuse sunlight, if any, comes in. And so they would be closer to the shelf life test we do compared to the light soaking test we do 1,000 watt per square meter. So on one hand, they will last longer. So that's something which is very interesting for developers of these technologies where stability is an issue for outdoors.
All right.
On the other hand, we found that if you take the same device, you've used it 1 year, and you measure it under sunlight and you measure it indoors, it's degraded more compared to outdoors.
Oh, really? Okay.
Because after a year or two, you create defects in the semiconductor at the interfaces. These will have a larger effect at low light levels. So it's still better to use them indoors because of the environment, but you need to be careful that, you know, the defects are produced do not affect performance too much.
Thanks. I think that's our last question I have is talking about perovskites, are
Yeah.
we having a chance of developing a recyclable or sustainable perovskite in the future? Like after this devices are degraded, can we reuse them after recycling?
Yeah, so we are working actually on a ministerial project which is funding us to do actually this. So we're teaming up with Milano Bicocca team. So we are giving them devices. They'll be extracting the various layers
Right.
and producing new precursors, which we'll then make devices with. And so one of the issues with perovskite is the fact that they've got very little amounts of lead, but they do have. And so recycling would be very important. And so there's been various works in the literature that show that recyclability is doable.
Right. Okay. That's
Oh,
great. Yeah. If we are able to produce a recyclable perovskite, it'd be really a breakthrough in the field, I would say.
yeah. Very interesting side of research.
All right. So I don't see any more questions from the chat box. So I'd like to thank Thomas again for the interesting talk, and thanks for joining us today.
Thanks so much for your invitation, and to everybody for being here to attend.
Thank you. Thank you, Thomas.
Thank you.